Okay, vectors day 2. Let's get a pen. What color is this? Let's use this color. You can tell me in the comments what color that is. I'm going to look at some scalar multiplication of vectors right now. And this isn't the overall note. Again, we're still sort of setting the ground rules for vectors. It's really just kind of tossing down some basics, the vocabulary. So there we go. So imagine that we had given 2 vectors, and A and B. Sketch vector W such that W is equal to 3A plus 2B. Okay, so just arbitrarily, I'm going to draw a couple vectors. Go this color, call that one A, and go this color, and we're going to call that one vector B. So I'll go back to my pen. So there's vector A, and there's vector B. Okay, so if I want to do 3A plus 2B, it is as simple as what it seems. So again, this is a thing of beauty for the smartboard. Turn it on infinite cloner here. So there's 1A, there's 2A, there's 3A, and then I have to add on 2B. All right, so there we go. There's 1B. Oh, forgot my infinite cloner. Come back here. Infinite cloner. There we go. There's a B and a second B. So then the resultant vector, which is, what happens when we solve this, the resultant vector starts here, ends there, and it is of course known as, well, this down here is vector W. So there's an A, there's an A, there's an A, and obviously a B and a B. Okay, so it's no more sophisticated than what it seems. 3A plus 2B, there we go. So, kind of define a little bit of a rule here. If we are given a scalar K such that K is a member of the real number system, then given K times vector A, it's getting kind of out of hand here. Let's clean that up a little bit. Given K times vector A, the length of K times A is equal to K times the magnitude of vector A. Okay, which, is an extension, and we can kind of state that a little bit more mathematically in that the magnitude, come back here, the magnitude of K times A is equal to K times the magnitude of A, which again is what you would expect. It's exactly, how you would expect it to go. But, some of the things that we're going to do in vectors, more when we get into 3-space vectors and algebraic vectors and vector multiplication, they don't always do what you expect it to do. So it's important that we kind of lay out the specific rules that do make sense, and then we're going to contrast those with the ones that are not necessarily as intuitive. Okay, so that's lovely. That's scalar multiplication of a vector. And then let's look at, I want to talk about collinear vectors. Now, some of you probably already know what this is, which is great. And I try to remember if I said anything about it yesterday. Collinear vectors, nothing fancy about collinear vectors. It is another name for parallel vectors. Okay, so the definition of this, and I'm going to give the formal definition. Vector A and vector B are collinear if and only if, so that's the double F, if there is some K, where K is a member of the reals, that is non-zero. Maybe I should put that in there. Some non-zero, I don't need an arrow there, is non-zero value of K, such that B is equal to K times A. So let's think about what that means. What that means is that as long as they're in the same direction, right? So, if I have a visual here, so imagine that I've got one vector that is, doing this, and then take another vector B, and, let's pretend that those are perfectly parallel or collinear. There's some number K that I could multiply this first vector A by to make it the same thing as B. So if this is A and this is B, maybe imagine that the magnitude of A is equal to, we'll make it really simple, is 8, and the magnitude of B is 2. Now they're in opposite directions. So what do I have to do? Well, the K value here in this particular example would be B is equal to negative 1/4 vector A. And so the negative is going to flip it the other way around, and the 1/4 is going to take its magnitude from being 8 down to being a magnitude of 2. So if you can express one vector as a scalar multiple of the other vector, that means that they are collinear. And if I tell you they're collinear, it tells you that. That's what the if and only if means. If we know one end of this, we know the other end is true. If we know the other end is true, we know this end is true. Okay, that's what if and only if means. So lovely. On we go. So let's look at our first sort of practical example, and this is where I'm sure you probably saw a solution like this if you're in Mr. Bagshaw's class, but you would have likely done this in Mr. Bagshaw's class with a scale diagram, whereas in here, we're not. We're going to go all math hardcore. So imagine the following. So here's an example. Given two vectors, I'm going to go with A and B. Not the plus, that's a bad and to use. Oh, crap. Given two vectors, A and B, where the magnitude of A is equal to 7 and the magnitude of B is equal to 3, determine the magnitude and direction of, what do we want to do? How about A plus 2B? So what I want to know is I want to know what the resultant vector is, so a magnitude and a direction. And you have to have both a magnitude and direction if it's going to be addition, because otherwise it wouldn't end up being a vector, of A plus 2B. Another piece that we need is the angle between A and B, is 30 degrees. Now, this, you might think, well, what exactly does that mean? The angle between. That means when the two vectors are placed tail to tail, the angle between them is 30 degrees. Now, this doesn't seem like all that hard a question at first glance, but as it turns out, it's actually, relatively spicy. Because we don't know where these vectors are, we don't know how they're facing. There's a lot of unknown here. And so when we go to answer this, we're going to have to choose our words very, very carefully. So, maybe if I just said, go ahead, go to it. Let's do that. I'm going to go ahead and I'm going to draw vector A and B. So here's my vector A. I'm going to say, there's my vector A. And that's a boring color, but we'll leave it as that. And then I'm going to say that I'm going to have vector B is here. Now, what do we know? Well, we know that vector A, here it is right here, and this is vector B, and we know that this angle in here is 30 degrees. Now, I really made this too big. I'm gonna shrink this up a little bit because we're gonna need some more space to play with than what I've got. So I'm gonna group that together, and I'm gonna shrink it up a little bit, put it down here, and then ungroup it because I'm gonna play with that. Grouping, ungroup. All right, so now that's how I drew it, but there's no reason that I drew it that way. I could just as easily have drawn B over here, and that still would be an angle between them of 30 degrees. Or I could have drawn A facing downwards and B facing down and left, or B facing down and right. So there's loads of different ways, just given this problem, that this could have been drawn. So when we go to answer the question, we're going to have to take into account that everyone's diagram is not necessarily going to be the same as everyone else's. So we'll see in a moment why that's a bit of a complicator. So there are my A and my B. That's not yet representative of what we're trying to find here. I want to add an A and two B's. Okay, well, I'm going to turn on my infinite cloner. I'm going to put, here's my A. Right there it is right there. And then two B's. I'm going to add them. Infinite cloner. So there's one B. Oh, that's not the right thing. Dang it. Come back here. Oh, I didn't infinitely clone the right thing. Oh well. Let's put that back. Clone. Clone. Okay. Put this guy back over here where it was. Clone. Boop. There we go. So there is the diagram for what's going on. Now, the resultant vector, which is what we're after right here, okay, the resultant vector is going to be this guy. Again, starts from where it starts, ends where it ends. So this is vector R. Okay, so this is vector R, and this is what I'm interested in. Now, could you figure this out with a scale diagram? Yeah, moderately, but it's not going to be exact. So I'm interested in more exact. If I think about the things that I know, well, I know this is vector A, and I know vector A has a magnitude of 7. So down I come. That's got a magnitude of 7. B has a magnitude of 3, and there are 2 of them. So this has a magnitude of 6. I want to find this magnitude, but not only the magnitude, I want to find the direction. Now, let's cast our mind back to some grade, I don't know, where did you first play with it, grade 7 or 8, but we certainly did it in grade 9 as well. This A vector, if it kept on going, we can see that the angle that it makes here is the same as this angle right here, right? That's 30 degrees. So that's 30 degrees, which means if that's 30 degrees, we know because a straight line is 180, that this interior angle is, of course, 150 degrees. Okay, so that tells me that that's 150 degrees. Hopefully you're like, huzzah, and you know at the very least now how to get the magnitude of R. The magnitude of R, this is a triangle. We have an angle sandwich, side angle side. So we can go cosine law. So I know, using cosine law, that the magnitude of r squared, so c squared equals a squared plus b squared minus 2ab cos c. So plus is going to be 6 squared plus 7 squared minus 2 times 6 times 7 times the cosine of 150 degrees. Now, I can actually have to calculate this, right? Cosine law. Now, I mean, I think probably everything for the end of the year, up until the end of the year, and including the end of the year, is going to be open book. I kind of think it pretty much has to be. Under normal circumstances, I would absolutely not on a test be giving you the cosine law. By this juncture, you sure as shooting should know it. But I'm going to go and calculate this. I'm going to have to make sure that my calculator is in degrees, because I'm doing this in degrees, which it is. And so I'm going to do then, that's going to be 6 squared plus 7 squared minus 2 times 6 times 7 times the cosine of 150. And so that's going to be 157.75. So I've got now 157.75. So 157.75. And that's what the magnitude of r squared is. But I don't want the magnitude of r squared. I want the magnitude of r. So the magnitude of r is going to be equal to the square root of that. So grab my calculator, do the square root. So to the exponent 0.5. Square root it, we're going to get 12.56. So the magnitude of vector r is 12.56 units. I didn't say what the units were, so it's just units. Lovely. Magnitude, not that bad, but if I add two vectors together, the result has to be a vector. And so for a result to be a vector, it means that it needs to have a magnitude, but also has to have a direction. Now, direction becomes pretty arbitrary. Like imagine that you can't say, oh, it's up and to the right, right? Because not everyone's diagram would necessarily have it as up and to the right. So imagine that I had a why didn't I get that one as well? I still haven't got it. Where? Oh, because the infinite collider's on. Turn the infinite collider on. Imagine that you had drawn it differently, and you may well have, right? There's no reason from the information that was given up here that you couldn't have drawn it. Oh, it didn't road, but like that. And so then the direction of the r vector, the resultant vector, would be different. So here's where we're going to have to go. It's important that when we're finding these directions geometrically like this, that you always want to find the angle where the resultant vector is tail to tail with one of the originals. Okay, so I'm going to do that. So I'm going to find this angle in here. Now, we have choices. Figure it out on your own. What would you do? I'm going to show you a solution in a moment, but we could do this in a couple of different ways. We could do it with cosine law. We know all three sides on this triangle now. So we could make this our side, our angle C, and do c squared equals a squared plus b, blah, 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 and we can use cosine law. Absolutely would be totally valid. And in fact, if there wasn't already an obvious obtuse angle in the triangle, that's probably the safer thing, because you've all taken grade 11 university and you learned about the ambiguous case in the sine law. There is no ambiguous case in the cosine law. Now, if there already is an obtuse angle that's going on that you're going to make use of, sine law you don't have to worry about. But if you like cosine law, I would bust out cosine law, but certainly sine law is the easier way to go. So I'm going to go sine law here. So I'm going to say that this is the angle I want right here. So I'm going to say that the sine of, I'm just going to call this theta, the sine of theta over 6 is equal to the sine of 150 over 12.56. And then I'm going to solve. I'm going to multiply both sides by 6, multiply by 6. That's going to go away, and then I'm going to do the sine inverse. So theta is equal to the sine inverse of this stuff. So the sine of 150 over 12.56 times 6. So grab my calculator and drop that all in. Okay, so sine inverse of the sine of 150 divided by 12.56 times 6. Close that down. And we're going to do that. We're going to get 13.82 degrees. So this is 13.82 degrees. And I need to kind of go like this just to make sure that 6 is included in the line. Okay, that looks like squared, not degrees. Degrees. Lovely. So again, that's good to know. But if we're going to answer this in a sentence, which I kind of would because we didn't have a diagram to begin with, we're going to have to consider this really, really carefully. Now, the resultant vector, here it is right here. If I were to take and slide a copy of that resultant vector back into our original diagram, and I think I need to make my original diagram back bigger again because I'm gonna want to do that. So here we go. Make this bigger again. If I put the resultant vector down in here, I'm going to clean up that stuff in there. I don't really need it now. Okay. Oh, I kind of want B there, although I guess whatever. That's still B. I have found that the angle that the resultant vector makes with A, because this is A, is 13.82 degrees. So this is 13.82 degrees. So if I were going to answer this, I could say, oh, the resultant vector is going to have a magnitude of 12.56, and it makes an angle of 13.82 degrees with A. You might think, huzzah, we've got it, we've nailed it down. Some of you probably are already seeing why that is not yet sufficient to describe it appropriately. Because imagine that we had another, I could have had a vector over here that made an angle of 13.82 degrees as well, right? So just saying it makes an angle of 13.82 degrees with A is not yet deterministic. It doesn't actually give us a specific, guaranteed we all understand what the answer is, right? So then we might think, all right, well, what are we going to say? It's to the right of vector A. Well, it is on my diagram, but if vector B had have originally been drawn over here, and there's no reason it couldn't have, then it wouldn't be to the right of vector A, it would be to the left of vector A. And then you're like, oh, well, it's clockwise. Well, only on my diagram. So we have to be really, really careful. So here's the language I'm going to use, and hopefully you can understand why it is what it is. So I would answer this and say the resultant vector R has a magnitude of 12.56. Is that what it was? I think that's what it was. Yeah, 12.56. And makes an angle of 13.82 degrees with vector A. Here's where we're going to be specific. I've got that wrong. Get rid of that. Makes an angle of 13.82 degrees with vector A toward vector B. Okay, so that ensures that we know that it's away from A toward B. So even if my B was drawn over here, the resultant vector would be in the right place. Okay, so the language is tricky. The math is not that bad, but the language in these scenarios is tricky. You have to be really, really careful with how you phrase these things. Okay, so there's some other stuff that under normal circumstances I would cover with this particular lesson with some geometric stuff. I'm going to leave that out because in the grand scheme, it's not all that fundamental to what we do. And we are going to have to be a little bit briefer with this unit simply because of the timing and the fact that I'm really only supposed to give you 3 hours of work between work and lessons. per week. So I'm going to assign some questions. I'm going to put them up on Google Classroom. I'm not going to write them down right now because I have it from a prior note, and I want to make sure that I'm not going to be asking you questions that I haven't explicitly taught the material of. Okay, so thanks for playing along and have a lovely day.